I now call to order the Society's 2487th meeting in what is now the 152nd year since its founding on March 13th, 1871. Good evening, everyone. Good evening. My name is Larry Milstein. I am the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends to tonight's PSW meeting and the lecture by Kathryn Huff on nuclear energy, advanced reactor designs. The Society is grateful to PSW full-year sponsors, PSW member Mike Helton and Helton Associates, LLC, and the Policy Studies Organization in cooperation with the American Public University. We are also grateful to PSW member Tim Thomas for his generous support of the Fall Lecture Series, and to the anonymous sponsor of tonight's lecture. Let's please give them all a nice round of applause. I want to note that PSW has been given a donor match gift by a generous supporter. All contributions now through January 31st, 2024 will be matched 2 to 1. So for every dollar you give, PSW will receive $3, your dollar, and 2 matching dollars, up to a total of $20,000 in matching contributions. So now is an especially good time to support PSW financially, although we are very, very happy to have your support anytime you care to give it. I am pleased to announce the following new members. Gary Portilli, a contractor broadly interested in science, particularly energy, housing, and transportation issues, who learned at PSW through the PSW Meetup Group. George DeVoe, a manager at Aptavian, interested in nuclear power, bioaptamers, security issues, and AI, who learned at PSW from a friend. Robert Marley, senior executive for R&D management at the U.S. Department of Energy, broadly interested in fundamental science, energy technologies, and science policy, who learned at PSW through the Cosmos Club, particularly through PSW member and Cosmos Club member Bob Hershey. And tonight's speaker, Kathryn Huff, who learned at PSW from an invitation to her to speak here tonight, and whose interests will be clear in some part from tonight's lecture. We welcome them all to membership. All members are entitled to a signed copy of Volume 1 of the Bulletin of the Philosophical Society of Washington. If you've not received yours, please come see me after the meeting. And if you're interested in membership, you can access a membership application on the PSW website by clicking on the Join button on the homepage at the upper right-hand corner. And if you are here in the Powell Auditorium, you can access the application using the QR code on the tables at the back of the room. Everyone is welcome to join. The main requirement is a genuine interest in science and a willingness to pay our modest dues. Recording Secretary Scott Matthews will now present the minutes of the 2486th meeting and the lecture by Missy Cummings on self-driving cars, the good, the bad, and the ugly. Is better than humans good enough? Scott.
Thank you, Larry. Good evening. On December 1st, 2023, in the Powell Auditorium of the Cosmos Club in Washington, D.C., President Larry Milstein called the 2486th meeting of the Society to order at 8:15 p.m. Eastern Standard Time. He began by welcoming attendees, thanking sponsors for their support, and announcing new members. Camille Lance then read the minutes from the previous meeting and the lecture by Robert Chuong on defining death. The minutes were approved subject to a minor addition suggested by President Milstein. President Milstein then introduced the speaker for the evening, Missy Cummings of George Mason University, Her lecture was titled Self-Driving Cars, the Good, the Bad, and the Ugly. The speaker began by briefly sharing her background, not only as a fighter pilot, but as a researcher focused on unmanned aerial vehicles. She discussed her shift to working on self-driving cars, emphasizing the similarities between the sensors used in drones and autonomous vehicles, and how she then shifted her focus to self-driving car policy and her work at the National Highway Traffic Safety Administration. The speaker then discussed the workings of self-driving cars, the digital nature of their controls, and the importance of building a world model for navigation. She discussed the sensor technology used in self-driving cars, such as radar, LiDAR, and computer vision, while addressing their limitations and challenges. She emphasized the importance of combining multiple sensors for comprehensive coverage. Cummings then explained the challenges of sensor technology, especially in adverse weather conditions, and she offered a cautionary note about the limitations of computer vision based on neural networks, which she said can have hallucinations when encountering unforeseen scenarios. She emphasized the misconception that internet connectivity is essential for autonomous vehicles, and also highlighted the potential dangers of relying on internet signals for critical decisions. The speaker discussed the concept of the stack in self-driving cars, representing the layers of information processing. She explained that the stack takes in data from sensors, formulates driving strategies, plans maneuvers, and executes actions, drawing parallels with human decision-making. The speaker then discussed disengagements, instances where humans take control, human disengagement, or autonomous systems relinquish control, autonomy-initiated disengagements. She presented data compiled by a number of companies on disengagements, particularly focusing on data from Waymo and Cruise. She expressed concerns about the transparency with which companies report disengagements. The lecture continued with a brief overview of crash odds ratios, comparing the crash rates of self-driving cars to human drivers in urban environments. The limited data and the need for more extensive testing, 250 million driver miles, to draw statistically significant conclusions was highlighted. She noted that she and others have not been able to access the raw data that Tesla has obtained on accidents and incidents for its vehicles with the autonomous driving feature. The speaker emphasized the importance of learning from mistakes, drawing parallels between human errors in driving and potential human errors in coding for autonomous systems. She recounted an incident involving a crash with a semi-tractor trailer due to a coding error caused by the failure to clear a memory buffer. Cummings then discussed an incident in San Francisco's Bay Bridge Tunnel, where a car abruptly slammed on its brakes, causing a multi-vehicle pileup. The phenomenon, she said, called phantom braking, can result when the car's system misinterprets its surroundings. She said that it is a widespread problem in autonomous vehicles. She went on to provide a detailed example showcasing a planning problem in autonomous driving, where a self-driving car, misinterpreting a right turn only lane, abruptly stopped, leading to a collision with a rideshare car. The speaker emphasized that this particular company did not embed physics-based models, which may have prevented the crash. The speaker emphasized the importance of updating models as the environment changes. An incident was discussed involving a self-driving car hitting an articulated bus, which was attributed to the fact that the computer vision system was trained on data from regular buses, leading to a miscalculation with an accordion bus. Cummings discussed the limitations of systems which rely on artificial intelligence, particularly in the context of self-driving cars. The speaker emphasized that systems like ChatGPT operate on statistical inference and lack sentience or the ability to discern truth from fiction. The speaker ended the lecture by proposing the need for better collaboration between humans and AI, leveraging their respective strengths. The lecture was followed by a question and answer session. During the session, questions were raised about the regulatory landscape for autonomous vehicles, and in particular, why they are still allowed on the roads. The speaker indicated that the main reason is that these systems are considered driving assists rather than full self-driving technology. Tesla's autopilot, for example, requires drivers to sign statements acknowledging their responsibility to maintain control and to comply with warnings. But people often become complacent and overly reliant on these systems, she said. A member asked about standards and testing for self-driving cars, particularly regarding non-deterministic AI. The speaker acknowledged the lack of standards and emphasized the challenges of testing non-deterministic AI, pointing out the absence of requirements for companies to demonstrate their testing. Another question addressed Tesla's decision to remove LiDAR technology and inquired about the potential benefits of vehicle-to-vehicle communication. The speaker explained that Tesla's initial avoidance of LiDAR was due to cost concerns. She referred to vehicle-to-vehicle communication as a, quote, nice to have rather than a necessity. The question and answer session concluded with a question about the positive aspects of self-driving cars, to which the speaker mentioned their potential effectiveness in specific applications, such as low-speed shuttles and last-mile food delivery. However, she expressed her overall skepticism about the feasibility of widespread adoption of fully autonomous vehicles for long-distance travel in the near future. After the question and answer period, President Milstein thanked the speaker, presented her with a PSW ribbon, a signed copy of the announcement of her talk, and a signed copy of Volume 1 of the PSW Bulletin. He then announced speakers for upcoming lectures and made a number of housekeeping announcements and invited guests to join the Society. He adjourned the 2,486th meeting of the Society at 10:10 p.m. Eastern Time. Temperature in Washington, D.C., 8 degrees C. Weather, overcast and light rain. Audience in the Powell Auditorium, 49. Views of the video in the first 2 weeks, 390. Respectfully submitted.
Thank you so much, Scott, for a very excellent set of minutes, which I have to say, everybody, this is his first time up here doing the minutes, so really exemplary. Thank you very much. Any comments, corrections, additions on the minutes? Hearing none, do I have a motion from a member to accept the minutes as read? A second? All members in favor? All members opposed? Hearing no opposition, the minutes are accepted as read unanimously, and they will be posted to the website in due course. We now turn to tonight's lecture by Kathryn Huff on advanced nuclear reactor designs for clean electricity. Kathryn is Assistant Secretary at the Department of Energy, where she leads the Office of Nuclear Energy. Before joining DOE, she was a professor in the Department of Nuclear, Plasma, and Radiological Engineering at the University of Illinois, Urbana-Champaign, where she led the Advanced Reactors and Fuel Cycles Research Group. She also was a member of the American Nuclear Society, where she was chair of the Nuclear Nonproliferation and Policy Division and of the Fuel Cycle and Waste Management Division. Her research focus is modeling and simulation of advanced nuclear reactors and fuel cycles, and she has long been an advocate of best practices in open, reproducible scientific computing, including leadership roles in such organizations as Software Carpentry, SciPy, Hacker Within, and the Journal of Open Source Software. Kathryn earned a BS in physics at the University of Chicago and a PhD in nuclear engineering at the University of Wisconsin-Madison. All questions will be fielded after the lecture during the Q&A session. Kathryn, the stage is yours.
Thank you very much, Larry, and all of you. I'm really delighted to be here. It's an absolute honor. And I was especially delighted to have dinner with many of you earlier. What incredible conversationalists you are. I will talk about a number of things here, but first I'll say, thank you to PSW for your sponsors, for your allowance of me to join you. I was asked to give sort of an overview that should help, distinguish advanced reactor types from one another, their ups, their downs, and the why of the physics behind different choices in different reactor designs. And so, what differentiates them, I think, is very important for you all to know as you have conversations about nuclear energy, because it's an incredibly relevant energy technology right now. You may know that just last week at COP28, the climate conference, our nation, along with 23 other nations and well over 100 companies, signed on to an agreement that by 2050 we must triple the amount of nuclear energy that we are using to power this world. And I think it's, by the end of this talk, I think, usually I would suggest, feel free to interrupt with questions, but I understand that that's it's not allowed right now, so you'll wait until the end of the talk. But if you look quite quizzical and puzzled and whatnot, I'll dive deeper, so feel free to use your facial expressions to indicate if you're puzzled. I'll keep an eye out. By the end of the talk, my hope is that you'll be quite conversant in the distinctions between design choices across reactor types and what's going on in the research and development space in the Department of Energy. I hope that at the very least, you'll be equipped with some of the key questions you can ask a reactor developer about their designs and understand their answer. So thanks very much. I do recognize that a number of you are nuclear engineers and physicists and nuclear physicists and chemists, and so some of this will not be new to you, but I'm hoping that some of it will be new to everyone. And at the very least, you'll get a nice review of nuclear reactor kinetics if you haven't seen it in the last few years. All right, starting at the top. Advanced reactors are often said to be a source of enhanced safety in our nuclear reactor space. Perhaps they improve waste management or have a more versatile power profile. Perhaps they'll be more affordable. But I'll have to paraphrase one Admiral Hyman G. Rickover, who, in the face of advanced reactor types long ago, many decades ago, said, there's a difference between advanced reactors and the reactors that are operating today. Reactors that are operating today, advanced reactors, I'll paraphrase him. Advanced reactors, they're cheap and they're using off-the-shelf parts and they're, gonna be smaller and more versatile and they're gonna be more affordable, but they're not being built today. Reactors that are built today, of course, are big and complicated, and they're stymied by seemingly simple engineering problems, and they are being built today. This is approximately still true, though there's a slight distinction. A number of advanced reactors are being built today, and I have actually this week, one advanced reactor has gotten a certification from the NRC to proceed with their construction for a test unit. We'll talk a little bit about the Hermes reactor very shortly, but I think the quote that has been so persistent in this space from Rickover is kind of nearing the end of its utility. All right, so advanced reactor designs. I promise it'll get more complicated very soon, but let's start with this. If you were going to design an advanced reactor, you would be facing a number of key questions. Primarily, what do you want it to do? We'll call these the performance targets. You have a number of things you can fool with to reach those performance targets. On the performance target side, a lot of folks want to focus on size. Maybe you want it to be quite small, perhaps even mobile, or you want it to be very big and provide baseload energy for a really large region of the country. You may want it to reach a very high temperature for combined heat and power applications for high temperature electrolysis to produce hydrogen, for applications in the chemical industry, for example, to produce advanced catalysts or other high energy intensity chemicals. You may want it to be extremely fuel efficient, or maybe you don't care about fuel efficiency. You may want that power to hit a particular mark. Maybe you're powering a data center in the tens of megawatts, or you're replacing a coal plant in the hundreds of megawatts, or perhaps a whole city or town or region in the 1,000 megawatt space. Finally, your reactor kinetics matter. What's reactor kinetics? We'll get in there. But this is fundamentally responsiveness to certain accident scenarios or reactivity transients, the way the reactor responds is inherent to its design. A number of materials choices that we'll go over, as well as geometry, isotope choices, neutron spectrum, et cetera, all affect these key performance metrics, including the reactor kinetics and the response to an accident. So over the course of this talk, my intent is to go over some of these choices you might make. And I'll comment then on how you get to the performance targets with different types of reactor design choices, whether it's your neutron spectrum, the coolant choice material that you choose, the fission isotope that you select, what kind of moderator, we'll talk about moderation in general, what geometries you might choose, what fuel forms you might choose, and how that affects some of these key performance metrics. So let's get started. All right. Just as a review, many of you do not need a review of nuclear physics. However, for those of you uninitiated, neutron interactions have two major types: scattering and absorption. In scattering, it can be elastic, like a billiard ball. It just bounces straight off one to the other. Or it can be inelastic, where it absorbs some of the energy, maybe kind of like two, squishy pieces of Jell-O bouncing across each other. There's maybe some energy absorbed in that interaction in a specific way. And then absorption. There's fission, which is the splitting of the atom, the release of energy and additional neutrons. Typically, there's capture, where maybe you absorb the neutron and a gamma particle is released. There's different kind of reactions where a neutron is captured and all kinds of other things can come off, whether it's a proton or 3 neutrons or 4 neutrons. Or you have alpha particles, which is the emission of a helium nucleus after the absorption of that neutron. All of the absorption reactions you can think of in the following way. A neutron is absorbed by the nucleus, and it enters an excited state. It's quite, highly energetic and unstable. It has too many neutrons, and it needs to figure out some way to kick off some of that energy. In some cases, it's an alpha particle. Sometimes it's 2 neutrons, 3 neutrons. Sometimes it's a gamma particle. And sometimes that atom splits. And the splitting of the atom is, of course, fission. The likelihood of that splitting is over here on the graph. We report it in neutron cross-sections. The likelihood, more or less, of a neutron interaction like this in different isotopes is presented here. These are isotopes that you would describe as fissionable or fissile. These are two different things. Fissile isotopes are the ones that are readily fissioned. Fissionable isotopes are isotopes that you can fission them, but it has to be a very high energy neutron. There's a lot of those. And fertile isotopes are the kinds of isotopes that can absorb a neutron and become a fissile isotope. All right. This matters in your selection of fuel isotope. So the key piece over here is that your options are approximately these: thorium-232, uranium-233, uranium-235, uranium-238, plutonium-239, and plutonium-241. In the thorium-232 and uranium-238 space, the cross-section is quite low. This is a log plot, and the probability is just quite low that this reaction will happen, the fission reaction in particular, right? But it's possible, and in fact, the higher the energy of the neutron, that's what this x-axis is, the higher the energy of the neutron, the closer you get to converging on the same likelihood that you would see in these other fissile isotopes. But uranium-238 and thorium-232 are fertile isotopes. They are not themselves usually used as a fuel because it takes such a high energy neutron to make them fission. Instead, you hope that they will absorb a neutron and become, in the case of in the case of thorium-232, it becomes uranium-233, which is, as you'll note from the graph, in this top set of fissile isotopes. Uranium-235, plutonium-239, also fissile isotopes. Does anyone see a pattern associated with this? Oh, I'm not supposed to take comments and questions. The odd-numbered ones are more likely to be fissile. The even-number ones tend to be fissionable or merely fertile. This is a feature of nuclear physics associated with instability and pairing, okay, inside the nucleus. Now, why am I showing you this graph? Well, you have to pick a fission isotope. Your first question for your reactor is which fissionable isotope or fissile isotope or fertile isotope am I going to use as fuel? Taking a quick look at this graph, it seems like you probably want to avoid these sort of less probable isotopes and stick with some that are very probable. And then you start to look at the structure here. A critical component of the structure of these cross sections is this resonance region, right? All of them seem to have it. You start up over here at high energy neutrons, and it doesn't really matter, and you have a pretty smooth path. Like the likelihood is quite continuous from very high energy to less high energy, et cetera. Then you hit these resonances where the nucleus itself is more likely to absorb neutrons of a particular discrete energy, all right? And you pass through these resonances, and on the very low end, you see there's some bumps. This lump right here is in what we would call the thermal energies, and it's nice and likely that a fission is going to happen. And so a critical component of the neutron fission reaction inside a nuclear reactor is slowing down the neutrons. They're born from fission way up here in the 2 MeV range, okay? And they have to make it either through this resonance region and create a fission inside the resonance region, or ideally, they come all the way down to these slower speeds and are captured in this very large and predictable resonance here, this big lump. The importance of predictability is, of course, control of the reactor and a number of other things, but slowing down those neutrons from where they're born to where they're most likely to be conveniently fissioned is called moderation. And we often refer to these slow neutrons as thermal neutrons because it's at this low range where they're in thermal equilibrium with the uranium atoms themselves. And so you can think of them as slow, and I'll refer to them as slow throughout this talk, but when I get a little lazy and excited, I'll probably refer to them as thermal, and that's what I mean. Thermal neutrons are in this slow region. Okay, so what you've learned is you probably want to avoid relying entirely on these less likely isotopes to fission and stick with the really good ones, uranium-235, uranium-233, plutonium-239. However, we do build in a number of these other isotopes through the capture reaction. So interestingly, as you fission uranium, of course, it creates fission products. The halves that are left behind, half of a uranium atom, is going to be part of the fission product set. And you can see a number of these fission products sort of grouped together in this one plot. So what we're looking at on the right-hand side here is the population of the fissile isotope that we're fissioning as a primary fuel, in this case, uranium-235, over fluence, so over time in the reactor. What happens is you start with uranium and nothing else at time 0. And then as you burn up that uranium, as you split uranium atoms, you build up other things. You build up continuously fission products. This is a log plot, so that nice smooth curve is basically a linear sort of growth of that fission products. Not quite linear because they do absorb other things. And then you have plutonium-239, plutonium-240, and you have also 241, 242, much less common. A critical component is that these slopes are different, and they're almost imperceptibly different if you aren't used to looking at this graph. But importantly, plutonium-239, it's created at a pretty high rate, but then it kind of starts to level off. And that's not just a function of the log plot, but also a function of fissions in plutonium-239 in a standard light water reactor. All right? So what's happening is you're creating plutonium-239 through the absorption of neutrons by uranium-238, one of the key isotopes in uranium-235-based fuels. It also has a lot of uranium-238. You build up more plutonium through the absorption and conversion of these neutrons into a plutonium-239. And then what happens is it fissions. It's now a fissile isotope, and it's in your reactor. 20% of the power generated inside a standard uranium-fueled nuclear reactor comes from plutonium fissions. from this process, right? So you may think you started your reactor design by choosing a uranium-based reactor, but in fact, you've chosen a uranium and plutonium-based reactor. This is a mere fact of the nature of this particular reaction set that we're describing here, and it's going to happen in most reactor types. No matter what fuel you choose, there's going to be some breeding, which is to say the creation of fuel, like plutonium, and there's going to be some burning, which is to say the splitting of those atoms into fission products, right? That mixture is a really delicate balance, but we were talking about baking earlier. You may choose a particular kind of balance for the flavor that you want, and we'll talk about that a bit, but I wanted you to have this basics. Now let's talk about the fission products a little bit. There is another important distinction between these main fuel isotopes. While the products that are generated in a fission, so you have a uranium atom, it's struck by a neutron, it splits in half. It actually doesn't split in half. You can tell by this plot, it tends to split in 1/3 and 2/3 buckets. What we're looking at here is the size of the resulting atom in nucleons and the percent yield. There are different colors for different source fissioning isotopes, and you can see that they're different curves. Uranium-233 tends to have fission products in the sort of first bucket dominated by strontium and zirconium, whereas plutonium-239 and uranium tend to be dominated by technetium. And there's a very dramatic difference, actually, in these slopes. And in the case over here in the higher level, they're a little bit closer, but you still see a significant difference in the fission products left behind in a U-233-driven reactor. So I just wanted to point out that another feature of how you choose your favorite fissile isotope is what kinds of fission products you are willing to have a large amount of. It may depend on whether or not you intend to recycle that fuel, whether or not you care about this. Most reactor designers are not going to care about this at all, but some are going to be really interested in trying to avoid some and not other types of fissile products. But it's pretty unlikely that. And this 65% U, 30% PU plot is intended to represent that kind of, mixture that you have in some light water reactors, where a significant percentage of the fissions are from plutonium, et cetera. Okay. Here's an even cooler way to show you that data. Importantly, I showed you the elemental data before in a single two-dimensional plot. This is actually, if you look in terms of nuclides, this is the heat map of the generation of various nuclides. You can read a nuclide chart in the following way. You want to focus on the number of protons on the y-axis and number of neutrons on the x-axis. And so every isotope in existence is plotted along this straight line. And you can create a whole bunch that don't appear in nature over the course of your operation of nuclear reactors, right? That's what's really cool about it. And this is them. And you can see that they appear in these two different sort of buckets. And so you can see why you might care more or less whether they create more or less of a certain thing if you have some target at the end that you might recycle for. All right. So making this choice, now we're diving really deep. All right. Once you've made this choice about your target fissile isotope, there's a critical component here where it drives whether you're having your fissions in that really fast range or much slower thermalized neutrons. Do you bother with slowing them down, or do you just hope to have a lot of fast fissions before you hit the resonances on the slowdown? And so that results in either a fast reactor, where you focus on the fast fissions, or a slow reactor, where you focus on the thermal fissions. It tends to be the case that this thermal type reactor that operates in a moderated space with slow fissions tends to be easier to design if you start with a uranium type fuel. And if you're really focused on breeding plutonium, it's going to be much more efficient to focus on fast neutrons. All right. So now you've got a little basic reactor physics. I promise it'll start moving a little quicker here. So in order to slow it down, let's say you choose uranium-235 and you choose, therefore, that it's going to be a thermal reactor. You have to figure out what materials to put in your reactor to slow down the neutrons once they're born. They're born at 2 MeV. You need to move them down into this thermal range. How do you do it? Well, there are a lot of different materials you can use in a reactor surrounding your fuel to moderate the neutrons. Now, standard nuclear reactor fuel in a light water reactor is a ceramic, so uranium oxide. It's in pellets in a big, long zirconium tube. And in the conventional nuclear reactors in the United States, that uranium is enriched so that the uranium-235 is a little higher in ratio to the uranium-238 than it was when it was dug out of the ground. That is around 5% U-235, 95% U-238. Anyway, this long tube full of uranium pellets, uranium oxide pellets, has to be surrounded by something to slow down the neutrons. Slowing down is this reaction, the scattering reaction, and we hope, that we're going to use that scattering reaction to lower the speed of the neutrons, right? So the neutron bounces at the atom, and then it bounces back off. Oops. And so, in a billiard ball scenario, it's important to note that 2 billiard balls of almost equal size are more likely to lose energy in that collision in such a way that you can slow one down by hitting another one of equal size. Think about this, all right? Think about those huge yoga balls, right? They're like bouncy yoga balls. Now think of like a tennis ball, right? If you throw a tennis ball at a huge, yoga ball, that tennis ball is going to go flying, right? You throw 2 tennis balls next to each other, they're going to bounce off of each other at a similar rate. And so you end up losing a lot of kinetic energy in the tennis ball to tennis ball scenario by sending the secondary tennis ball off into its other direction. But you don't in the big bouncy ball scenario. It works a little better if you're thinking of mass, but I think it's illustrative in these kind of elastic balls. All right, critically, therefore, you can choose materials that are similar in size to neutrons, right? Anything like a hydrogen, really low in the periodic table, are going to be much better at reducing your speed. Importantly, what we're showing you here is graphite, right? Neutron reaction probabilities in natural uranium and graphite. You can see through this case, there's a probability of capture in blue, so you lose the neutron from the reaction. There's a probability of fission in uranium in this sort of orange color, and then there's the probability of capture in the graphite, right? So you want to avoid capture in the graphite and in the uranium, and you want to maximize the probability of fission. And so, way up here it makes a lot of sense, and then way down here it makes sense. You want to get this capture to fission ratio as fission-y as possible. So that's how you choose a moderator. Generally speaking, in light water reactors, we choose light water, unenriched water. A critical component of making your decisions is whether or not your uranium atoms are enriched in that fuel. In Canada, they don't enrich the fuel. Instead, they enrich the water. And so they scatter the neutrons more effectively using deuterated water, deuterium-2O, if you will. All right, here's a whole set of parameters for the kinds of choices you might make. Hydrogen itself, just all by itself, if you wanted to moderate your reactor with hydrogen gas, that would be a totally reasonable choice. Or, in this case, it's just H, but, H2 would do the trick. Deuterium on its own also would do pretty well. H2O, deuterium-2O, helium, beryllium, carbon, like graphite, right? And then you can compare it to a really heavy atom, and you see it doesn't do very well. So, and how do you see it doesn't do very well? This is a bunch of data about the atom itself and numbers of collisions, et cetera. The key parameter is this one, and it's the sort of loss of energy per collision in terms of lethargy over the number of absorptions. So you try to maximize the amount of energy loss and avoid too much of the absorption and loss of an actual neutron. And so you can see, wow, some of these are really, really good at their job. And there's water, our sort of favorite, right? But you can see that the choices you make about how to slow down these neutrons, you have a variety. And we'll see in a second when I go over all of the different advanced reactors that are out there this year and last year and the last few decades, that every single one of these moderators are an option facing the advanced reactor community. And a lot of them are exploring that space, right? There are even others like lithium, et cetera. So we'll talk about it. All right. So I've already explained all of this a number of times, but we're now going to dive kind of deeper into another one of the parameters you need to choose, which is a more complex dynamic one, specifically response of this reactor to specific accident scenarios or off-normal conditions. We tend to call this reactor kinetics. Okay, so I'm going to go back over the fission reaction, but describe to you then the time component of that fission reaction, and then we'll get to what it looks like to choose materials and geometries to maximize the kinds of behaviors that we want. And if I were allowed to sort of like engage with the audience, I'd say, what kind of behaviors do we want? And the kinds of behaviors that we want are really stable, negative feedbacks to any increase in temperature or power, because you don't want a runaway reaction. The whole point of a nuclear reactor, it's a very complicated way to boil water, right? And whenever we're boiling that water, we don't want that temperature to build on more temperature and cause more temperature, because then you get a runaway temperature, right? You might even melt the fuel, call that a meltdown, right? Ideally, you would like the kind of scenario in which an increase in temperature causes a decrease in temperature. This would be a negative feedback. Or an increase in boiling causes a decrease in boiling, also a negative feedback. Increase in power causes a decrease in power. And that way, you can target your design to a specific power and be confident that it'll stay steady, right? And you can do this with passive safety through physics. So that's why I've explained all these materials differences to you. It's because we're about to talk real kinetics. All right. Obviously, neutrons are white because they are neutral. Protons are red because they are not neutral. They have a positive charge. This is our cartoon of a uranium atom. It is struck by a neutron. Maybe it's a thermal neutron, a slow neutron. Maybe it's a fast neutron. Either way, that it fissions. And kapow, it creates some heat, energy, and a bunch of neutrons. 2 to 3 neutrons is standard, not 2.5, because neutrons don't fall apart. They are quite fundamental in this way. And then what we want to see is sort of critical to this is that the cross-section in Barnes, the probability of this fission, you can think of this cross-section in Barnes as the probability of a fission. It depends on a whole bunch of other things. It depends on the energy of the neutron coming at it. It may depend on the material of that particular, it may depend on sort of the angle at which things are happening. So that's R theta. It may depend on the isotope that it's hitting. It's going to depend on temperature of the isotope, and I'll talk about the temperature of the isotope mattering in a minute. But it depends on a whole bunch of things. How the neutron strikes the atom, how fast it's moving, where the atom is, etc. Okay. Because it depends on all those things, these can create feedbacks. This is the source of the feedback, is the dependence between the energy and the temperature and the isotope on the probability of a fission itself. So fissions can cause changes in temperature, and changes in temperature can cause changes in the probability of fission. So you can see where these feedbacks come from. I'll show you another diagram in a second, but this is really important for the accident transients. Okay, now I told you that we create 2 or 3 extra neutrons. Those 2 or 3 extra neutrons in a chain reaction, of course, are meant to create more fissions, right? Ideally, one will reach a generation to generation ratio of exactly 1. A critical reactor has a scenario in which one fission causes another fission and then causes another fission in line. One fission does not cause 2 fissions, as is in this diagram. This diagram is a supercritical reactor, which is to say it goes above K = 1. It's a scenario in which you have a growing reaction. A subcritical one would be as if that each fission caused slightly fewer fissions in the next generation, right? So you have to hit like exactly one neutron of these 2 or 3 makes it to create a next fission. And this is all a carefully balanced dance between the fuel material and the moderator material and the temperature of the reactor and a number of other things. So in the context of kinetics, the behavior in an accident, what we're trying to avoid is a scenario in which we accidentally change this probability so much that we take a critical reactor, which has 1 fission for every fission in each generation, and we accidentally make it a supercritical reactor. Or if we do really badly, we make it what's called a prompt supercritical reactor. And so it goes way, way, way over power quicker than we're able to respond. And we'll talk about prompt versus delayed in a second. All right. Oops. All right. So I said K equals 1. That's what we want. This is criticality. This is actually the neutron multiplication factor. It's the number of neutrons causing a fission divided by the neutrons produced by the fission. You want it to be 1? If it's greater than 1, then that means that there's more neutrons causing fission than were produced in the last one. So, you can see what I just described verbally in a very simple equation. Reactivity is the difference between the actual criticality and 1 normalized by the criticality itself. So this is basically delta K over K. All right. Reactivity is the likelihood of going supercritical or going subcritical or staying critical. If reactivity is 0, then K equals 1. All right? If reactivity is positive, then we have a supercritical scenario evolving. If reactivity is negative, we have a subcritical scenario evolving. All right, a number of things matter to all of this. The change in reactivity is even more important. You can change the likelihood of whether you're going to be supercritical or subcritical over the course of this reaction. And one key feature is that temperature that I described. I said earlier that we want it to be such that if the temperature increases, the temperature should try to decrease. We want to have a natural physics reaction that when the temperature goes up, the temperature goes down. A way that this happens is in the resonances. So I showed you all those plots with the squirrely lines and those resonances where specific energies of neutrons are captured more readily by the nucleus. Temperature affects the shape of those resonances through the Doppler effect. All right, we're going to take just a brief moment. How many of you have heard in any context of the Doppler effect? Yeah, it's in astrophysics, it's in sonar, it's in like all kinds of stuff, right? It's in traffic. It's in a million different things. Okay, the Doppler effect in the context of these resonances is basically this. As the temperature of the atoms increase, they wiggle more, right? This is the definition of temperature, right? You heat up a reactor, the atoms wiggle more. If they're wiggling, they're now moving in relation to the neutron that might strike them. Now it changes, therefore, the effective speed with which the neutron is striking them, much like the frequency you see from a blue star versus a red star, sort of Doppler shifted blue, Doppler shifted red. Or the sound you hear is different as the ambulance is approaching you versus as it's driving away, right? This is extremely similar, and the effect is that it widens the resonance. It widens that part of the probability graph in which we can hit the right energy, and the neutron is absorbed by the nucleus, and maybe it creates a fission. Okay. The Doppler effect is almost instantaneous. As the temperature increases in the reaction, it happens right at the fuel. And as that temperature increases, the Doppler effect is immediate in the nucleus. And so it's a really strong opportunity for feedback, okay? Some Doppler effects are going to be positive, some Doppler effects are going to be negative. Widening and shortening is a nice feature, right? The fact that the probability, when it widens, it also goes down in that middle bit of the resonance. But different materials are going to have different resonances that you want to either Doppler or not Doppler. Anyway, the temperature feedback can be a combination of Doppler and what we call the void coefficient. There's a number of other possible contributors to the Doppler, to this sort of effect where we want to change the reactivity as a function of temperature. But the most important two are this Doppler effect and whether or not you're creating voids in one of the materials. Voids, of course, are just an absence of molecules. In water, for example, when one heats up water, it boils and it leaves voids in the water. Any kind of change in density in the material changes the likelihood that you're going to run into an atom as you move along if you're a neutron. And so we call this the void coefficient. Some folks would call this the material density coefficient, but I prefer the void coefficient. Anyway, if the temperature feedback coefficient is negative, then you have negative change in reactivity as a function of temperature. If it's positive, then it's positive, and same with voids. They can compete with each other, so you might choose to design a reactor that has a negative temperature coefficient with respect to Doppler and a positive temperature coefficient with respect to voids. You might not choose this intentionally, but maybe there are other features of your coolant that you like, that you'll keep around, even though it has this downside of creating more reactivity when it boils. This is the case sometimes with sodium-cooled fast reactors. Okay. I hope this is clear as mud. All right, so we're almost done with our kinetics 101, I promise. The reactivity, All right. The reactivity is this sort of, the feedbacks are some sum of those coefficients of reactivity, Doppler, void, whatever, and the change in temperature itself. And the sum of these things, plus any kind of external reactivity that you insert, will result in a total new reactivity. And then it'll drive a change in neutron population in the next generation, which will then drive the power of the reactor and therefore the temperature of the fuel. Power in reactor equals temperature of the fuel. We get power from heating up the fuel. That's the kapow in the fission diagram. That fuel component may heat up all the things next to it. Maybe your fuel is surrounded by coolant, and your coolant is surrounded by some reflector, and the reflector is surrounded by some steel container. And all of those things change in temperature, and they change in likelihood of cross-section, and now you've got a new change in temperature to drive your change in reactivity. Now, the thing I'm not describing here is the external reactivity. This is where the accident happens, right? You do nothing, and nothing changes in terms of the temperature. None of this happens, and you have no change in reactivity. It's all just reactivity equals 0, reactor's going on just fine. But what happens sometimes is that maybe you take out some part of the reactor. For example, what we call a control rod. You might pull a control rod, increase the reactivity to increase the power of the reactor, and now you change the whole situation. And so all these things work together. And what you want to do is identify materials that drive the reaction toward a stable state. So one interesting problem with all of this is that it does not happen instantaneously. Some of it happens instantaneously, but some of it happens on a delay. And if you ask me, it can be a problem, sure. It makes the whole thing very complicated and stops being a sort of interesting, like ordinary differential equation and starts becoming like complex analysis. Okay, those of you who've done complex analysis, it is really annoying to find those roots, et cetera, but that's how we solve reactor accident equations. It is because that fission product, half of the uranium atom, for example, about 50-something of them tend to be so unstable at the end of this splitting that they kick off a neutron a little late. They don't do it instantaneously. There's the neutrons that come out of the fission initially, right? But then you're left with these fission products, some of which are somewhat unstable, and then they kick out a neutron. And now that's contributing somewhat later to the whole reaction neutron balance that we talked about, right? These are called delayed neutron precursor atoms, the fission products that tend to kick off a delayed neutron later. Delayed neutrons, so first of all, the prompt fission reaction happens in 10 to the negative 14ths of a second, all right? So a fission happens, bam, now you've got neutrons. You've got energy, it's all happening at 10 to the negative 14 seconds. except for these delayed neutrons, which now join the equation up to a minute later. Bromine-87 has a decay half-life for this kickoff of a neutron 57 seconds or something later, right? Pretty gnarly. So now it's a dynamics problem. And we describe this in a number of ways. We have the decay half-life, right? Bromine-87, we said it's like almost a minute, and which group it's in. We couple all these things together, and we get a kinetics equation. It's almost 9 p.m. I won't make you sort of think hard about this particular equation, but this is what we call a stiff differential equation. And this is a version of the equation I can write on the slide because it treats the entire reactor as a point. It completely ignores geometry, and it's the only way you can write it down on a single slide. It depends on a number of things, and that's the point of me showing you this. The reactor power itself is the thing you're solving for. It's this first equation, but it relies on a number of things. It relies on the reactivity, of course, which itself depends on the time, the temperature of the fuel, the coolant, the moderator, the reflector. It depends on the time now because of those delayed neutron precursors. It depends on the fraction of neutrons that are delayed, the fraction of delayed neutrons from each precursor group, the concentration of each precursor group, the generation time. So this mean generation time I won't go into, but it's broadly the time constant of the reactor. The decay heat from various fission products, et cetera, et cetera, et cetera, and the temperature of each component directly, not just as a function of reactivity. So it appears twice the temperature. You can see this matters. The reason I bring this up is that this is where reactor design becomes actually hard. Right? You actually have to think extremely carefully about the balance between different materials in your reactor in terms of how it'll respond to an accident. You can load it up with all kinds of negative reactivity feedback options, but then your reactor might never turn on, okay? You can load it up with all kinds of positive things, and then you have a real scenario on your hands. What you want is something really straightforward, like this. This is actually accident transient scenario for the pebble bed fluoride salt cooled high temperature reactor. Kairos' Hermes reactor that just got this construction permit from the Nuclear Regulatory Commission is of this type. I had the honor and pleasure of working as a postdoc with that group and ran some of these accident transients. It's important for this lecture because I think you need to see what it looks like. You can insert reactivity, which is to say, induce an accident, increase the power unexpectedly by a dramatic amount over the course of like a second in this case. That is called a ramp reactivity insertion. And that reactivity, it grows really dramatically, right? You go from 0 all the way up to this sort of fractional amount. And the power responds. It goes way up. In this case, it triples. But then it immediately starts shutting itself down, right? And not a single human interaction is required. The physics itself drives the power back down, right? There are plenty of reactors that do this today in many ways, right? And I think a critical piece of making sure that you understand why advanced reactors are what they are and where they should go with their futures is that they should have this passive safety. They can come in different sizes. People are designing microreactors in the 20 megawatt space. People are designing small modular reactors in the tens or hundreds of megawatt space. People are still building large-scale reactors like the AP1000s out in Georgia in the 1,000 megawatt space. The idea here is that they're going to be right-sized for different kinds of applications. But they're going to have different coolants. They're going to have different fuels. We often talk about reactors in the nuclear reactor space based on their coolants. It's a weird naming convention, but we refer to the standard conventional reactors as light water reactors, as if that's the only material in the whole thing. It's not. It's just extremely important when you think about this kinetics question, when you think about whether it's moderating or not. And therefore, you get a notion of neutron spectrum, you get a notion of kinetics, you get a notion of the fuel type you can use with it, all from just knowing the coolant. So now you know that this is why we call them this way. All right. A variety of different reactors are sort of on deck right now. Light water reactors are pretty standard. They're getting smaller. There's a lot of interest in small modular reactors. High temperature gas reactors, they use helium as both a coolant and a moderator. We saw helium in our graph before. That's the idea behind high temperature gas reactors. Molten salt reactors use chloride or fluoride salts. In the case of fluoride salts, it might be a fluoride lithium beryllium salt, really maximizing that moderation. In the case of chloride salt, they avoid that moderation with heavier atoms in the salt and try to aim for faster reactors. Liquid metal. This is typically a metal-fueled, metal-cooled reactor, like a sodium-cooled fast reactor. Now, some of you are saying, wait, isn't sodium a salt? It is not a salt, it's a metal. This can be very confusing, but sodium on its own is a metal. So when we talk about sodium-cooled fast reactors, we are not talking about salt reactors. And then finally, heat pipes. This is just a clever way to get the heat out using static capabilities. I probably need a time check. It's like 9 p.m., so I should probably move a little faster, huh? Okay, light water reactors. Let me just walk you through a brief geometry and you'll get a notion. So the control rods are absorptive rods that you stick in just to suck up neutrons, all right? That's the idea, so keep that balance. The reactors are typically below grade. You have a containment vessel around the whole thing, and the fuel is just this yellow part. It's nice and hot. The water flows through, out, exchanges heat, runs a turbine, comes back in cold, etc. In a high-temperature gas reactor, you're going to have a scenario in which the control rods probably come in from the top. You may use graphite as a moderator. Again, that's carbon. And your fuel may be in a prismatic shape, or in some cases, in a pebble configuration. I'll show you a picture in a minute. Molten salt reactors, it's just a liquid pool, or sometimes it's a series of pipes. In this case, it's a series of pipes, and you have control rods coming in from the top, moving around a molten salt. That fuel salt has the uranium dissolved in it. And so the fuel is your coolant and your moderator all at the same time. Many people will tell you that a molten salt reactor can't melt down. Unfortunately, that's because it is already melted down. So, be careful. Liquid metal reactors, liquid metal reactors have a similar shape. Importantly, say it's cooled by sodium, right? Your core is here, you have liquid metal moving around, you need a heat exchanger. An excellent feature of these is that they're going to be very fast. They don't moderate very well. You get really fast neutrons. You may breed a lot more plutonium, for example, in such a reactor. The reactant, scenario is such that you will. But there are some downsides. Sodium, for example, is hard to see through. It's a metal, right? It's also pyrophoric with water. So it burns in contact with moist air. This has happened. So there was a commercial sodium-cooled fast reactor in Japan called Manju, which did have a couple of minor fires. And, not a huge radiological problem, but extremely challenging operationally. We have a really excellent design that DOE is funding called the TerraPower Natrium design. This is Bill Gates' reactor, and it's based on this technology. Heat pipe reactors are designed to be very small without a lot of moving around fuel, and they use the technology that chips use to move heat from one end of a static pipe to another using capillary action. And so you can take the heat out of the reactor straight to the other end of the pipe using really long capillary action. All right, I recognize that I'm probably coming up on time, but do I have plenty of time? I don't have until midnight. All right. Oh yeah, I guess I started. Sorry, I can't count. All of this and I can't count. Okay. So the TerraPower Natrium reactor is that design. It's Bill Gates has led a company called TerraPower. It has a couple of reactor designs. The one that DOE is funding in a really big way is demonstrating this reactor technology in Wyoming at the site of a retiring coal plant in Kemmerer. It is a sodium-cooled fast reactor, and just to confuse everything I just said about salt and sodium, it has attached to it a solar salt energy storage capability. So it's a sodium-cooled fast reactor, which is a metal, not a salt, and it has a salt energy storage capability attached to it so that without changing the reactor power, you can change the power that you provide to the grid by alternating how much thermal energy you're storing in the salt. Very clever, but has created a great deal of confusion among the public about what's salt and what's metal and what's sodium. So I implore you, brilliant leaders, to help us with this conundrum in the public eye. Anyway, the cool parts of this design, so you're looking at this design and you're saying, where's the reactor? It's down here. So below grade, below the ground that is, one would put the reactor core and any control rods and systems. Hot salt flows out to the hot salt storage system. Cooler salt flows in to exchange heat, and you have this nice solar salt out here well outside of the reactor space. You have a turbine, you've got a turbine building, you've got a place to store your spent fuel over here. It's pretty exciting. A big crane over here, big crane over here, all just for moving the fuel around. And this part has to be pretty much water-free, okay? Which is not hard, it's small volume, and we've successfully operated a sodium-cooled fast reactor here in the United States, actually a couple, but I think the most interesting one is called EBR-2, which was built much like 51 other experimental reactors. It was built in Idaho decades ago. The EBR-2 reactor was a sodium-cooled fast reactor, and it was really fascinating because they did a great experiment where they showed off this reactor kinetics. They brought a bunch of political bigwigs to the control room out at Idaho, in the Idaho desert, to the EBR-2 building, and they stood in the control room, and they said, all right, we're going to induce an accident in the reactor. And they pulled the control rods, and they stood there and watched as the reactor increased in power and then brought itself back to a stable state. I know. Isn't that exciting? It's so scary. And this was decades and decades ago. We in the United States know how to do this. We've done it before, and it's clear now through this company we will do it again. This will be a commercial reactor, however, unlike the EBR-2, which was largely an experiment. It did, however, EBR-2, power much of the Idaho National Laboratory site during its operation, and we recycled its fuel over 8 times. We're still using fuel that was used in the EBR-2 reactor. We're downblending it right now to make high-assay, low-enriched uranium for our next generation set of reactors, possibly even this one. Pretty cool. Okay, the other demonstration reactor that we're funding in DOE is the X-Energy XE100 high-temperature gas reactor. It's helium-fueled. It's helium-cooled, and it is a pebble bed-fueled reactor. It's interesting because, here's the control rods. They come in and out. This is how you control the reactor. You either absorb neutrons or you don't absorb neutrons, and you do this mechanically. It's a good thing we have delayed neutrons, because otherwise you wouldn't have time to do this. That's the miracle of delayed neutrons that I'm not sure I actually ever got to in my discussion. If we did not have delayed neutrons, we would have no chance of designing a reactor that perfectly avoided reactivity transients that run away from us, because it would all happen at 10 to the negative 14th seconds. Delayed neutrons give us a chance to control the reactor. Anyway, here are the control rods with which we do so. And in this case, this is the core itself. And it's full of thousands of pebbles of fuel. I'll show you an example in a bit. And those pebbles are cooled by helium moving back and forth across this space. So it goes up and then in and then up and then out. Right. And then pretty high. It depends on the reactor design. I don't know for this particular reactor, but you're looking at extremely high pressure, sort of, megapascals, I think. Yes. Higher pressure than light water by at least twice, depending on the reactor. At least twice. Usually much more than twice. All right. The Kairos power reactor that we talked about earlier, having this nice accident transient, this is a pebble-fueled, salt-cooled reactor. Very cool. So it uses a clean salt to cool the fuel. And it's fluoride salt. So it uses fluoride, lithium, and beryllium to moderate the neutrons. And it has all of the fuel in what's called triso fuel particles, which I'll show you in a minute. It's just like the X-Energy XE100 triso particle fuel, with just some slight differences. Westinghouse is building an eVinci reactor under DOE cooperation. They've just created a heat pipe factory out there outside of Pittsburgh, and the intent for this reactor is to be quite small. The previous two are in the hundreds of megawatts. This one would be in the 5 megawatt range. The Banner reactor is a BWX reactor in the microreactor space, high temperature gas cooled microreactor, but very small in the tens of megawatts. Holtec, we're supporting to reduce the risk of their commercialization. It's a small modular light water reactor. Holtec is a nuclear company that's historically been focused on decommissioning nuclear power plants, and they happen to have a whole factory in Camden, New Jersey, which you can take the train to, it turns out, where they create casks for spent fuel. And they've been doing this for decades, right? Those same casks for spent fuel have given them a lot of experience in creating what could easily be the pressure vessel for a small modular reactor. So their intent is to have a small modular reactor factory there in Camden with this small modular light water reactor. Molten chloride fast reactor, a Southern company is building this along with TerraPower. Bill Gates' company's second design is the molten chloride fast reactor. This is a fast spectrum, so the neutrons are fast, you're having your fissions in the fast range. It uses a chloride-based salt in order to achieve this. It doesn't moderate down the neutrons. And it looks like this. It's a big pot of salt right in the middle, right there, and a whole bunch of pumps. Pretty neat. We're running an experiment out at Idaho, our nation's nuclear flagship laboratory under my office. That's called the Molten Chloride Reactor Experiment, along with Southern Company and TerraPower, and it's going to be pretty cool. All right. There's a sodium-cooled reactor facility from Advanced Reactor Concepts that we're supporting. It's really similar to the TerraPower reactor, but quite small. Again, below-grade sodium, water-free zone, and then a bunch of other auxiliary stuff. Horizontal compact high temperature gas reactor from MIT. This is very conceptual, but their intent is to demo in the mid-2030s. The fast modular reactor from General Atomics, again, a concept to mature for potential demo in the mid-2030s. This fast modular reactor combines a number of these features, including it's a gas reactor, but fast spectrum. All right. NuScale Power is the first Nuclear Regulatory Commission certified U.S. small modular reactor. The idea here is it's a shrunken version of a light water standard reactor like the 93 reactors we have operating here in the U.S. today, but it combines not just the core features of a light water reactor, but also puts the heat exchanger right there in a single power module. So what is usually outside of the reactor core space, outside of the pressure vessel, that heat exchanger, they put inside the module. So that's the interesting feature of that reactor. And then Marvel is a microreactor we're building out at Idaho, just with Idaho National Laboratory oversight and guidance. It will be a DOE-authorized reactor. So through the Secretary of Energy's authority, my office gets to authorize this reactor as if it's sort of the NRC of National Laboratory reactors. So that's pretty cool. We haven't used this authority in many, many years, and I'm looking forward to it. All right. I do want to just talk briefly about fuel forms. I promise it'll be pretty quick. So I keep talking about uranium oxide fuels. I described them earlier. I just want to be extremely clear about what we talk about when we talk about this. Uranium oxide fuel pellet standard in a conventional reactor looks like this. And then you put it inside a cladded fuel rod, and then you put it inside you collect a whole bunch of these, and they're quite long, meters and meters tall. Each little pellet has the equivalent energy of about a ton of coal. You have a bunch of these assemblies in a reactor, and it operates without stopping, without refueling, for 18 months to 2 years. And then you take out about a third of that fuel and replace it with fresh fuel. If you think hard about it, the volumes here are pretty critical, but it's a pretty nice kind of clean space. So when people talk about nuclear waste, I will say commercial spent nuclear fuel looks exactly like this. This is commercial fresh nuclear fuel, and it's maybe a little wetter, sometimes with a little bit of crud on the top, but this is what it looks like. So commercial spent nuclear fuel is not the Homer Simpson glowing green goo that you have been led to believe. Okay, we're trying to advance these fuels in the Office of Nuclear Energy. Uranium oxide fuels can be clad with more clever materials. They can be doped with clever chemicals that enhance their accident tolerance through kinetics, through materials choices, through isotope choices, all identifying reactor physics that'll drive accident tolerance. Some of them increase the temperature with the temperatures that these fuels can withstand. Some of them improve the reactor physics through kinetics. There are a number of different ones. Fecral is an iron-based clad. Chromium-coated M5 cladding basically takes the exact same clad that we use in every reactor really today and adds some chromium coating to it. Chromium coating zircaloy adds a sort of clever clad with chromium coated with a chromium coating on it to reduce corrosion. And General Atomics has used silicon carbide, which has an incredibly high melting temperature. The way that we make it, just for awareness, is that you have to create a gas, convert it into a uranium oxide, then press it into pellets and sinter it, and then you put those pellets into a tube. So that's the sort of fuel cycle process. In order to get to this, you have to mine it out of the ground and then turn it into yellow cake, which is uranium U3O8, and then you have to convert it to UF6 and enrich it. All right. This is what Bill Gates' metal fuel looks like for a sodium-cooled fast reactor. Looks familiar, right? It looks really similar to a light water reactor fuel, except hexagons are the bestagons. In nuclear engineering, a lot of hexagons appear. There's just a really nice sort of rectilinear function where you can make all kinds of shapes with hexagons in regular pattern. You see it all over nuclear energy. Anyway, hexagons are the bestagons, and so this natrium fuel is really interesting. The one interesting feature about that you can recognize metal fuels typically by this wire wrap, which is often used to sort of make sure that the metal coolant has a sort of flow around the cladding in a predictable way, which is less necessary in a pressurized water reactor. All right, I'm getting close. So, one of the coolest fuels ever is tristructural isotropic fuel. We in DOE have helped create this fuel through decades of research. You, as federal taxpayers, have contributed to it. And what it is basically a containment structure around a teeny tiny chia seed-sized particle of uranium. We take this teeny tiny little particle in the micron range, right, and then you coat it with buffers of silicon carbide and pyrolytic carbon until you have contained it with some of the hardest material known to man. Those silicon carbides can contain the fission products to incredible temperatures for extremely long periods of time, well beyond accident conditions. And so you've created tons of little containment structures in your fuel. And so the dangerous thing, those fission products that are very radioactive, and they've been created all over the table of the nuclides, well outside of the natural table of nuclides, those are all kept inside of that silicon carbide. These are used in a number of the reactors I've just showed you, all of the gas reactors that I showed you, plus the Kairos Power PBFHR, that fluoride salt cooled high temperature reactor that's cooled by salt. These trisoparticles can be embedded in graphite pebbles or embedded in graphite cylinders. And here's what a pebble looks like. It's nice and shiny, a graphite pebble. And here's the inside of a graphite pebble full of trisoparticles that's been irradiated in a test reactor. And you can see none of them are broken. And this one has seen quite a lot of high temperature and fission product expansion. This is what we put in the X-Energy XE100 reactor, for example. These pebbles, they're about this big, the final pebble, and so have hundreds and hundreds of thousands of tiny particles. The Ultrasafe Nuclear Corporation has a similar reactor design that's a high-temperature gas reactor, and instead of using pebbles, they actually have a big graphite block and have drilled big cylinders in it, and they drop cylindrical versions of those pebbles into the tubes. So this is what you would call a prismatic gas reactor, but inside are more trisoparticles. Here's actually what I was just trying to describe verbally. you take your TRISO fuel, you fill a fuel compact, and then you put the fuel compacts in these red channels in a large graphite fuel block. Why do you need graphite? Moderation. You're trying to make a thermal reactor, you need something that's going to bounce the neutrons around and help them lose energy. All right, salt as fuel looks kind of like this. It's not very exciting, but I think importantly, this is exactly the salt that would be used in a fluoride salt-cooled high-temperature reactor. You remove the uranium, and now it's the salt that's cooling the fluoride salt-cooled high-temperature reactor from Kairos. We just made some really cool salt, so I wanted to show you. So out in Idaho, we do a lot of things. I run a $1.8 billion Office of Nuclear Energy. We drive a lot of research and development. I get really excited about most of the research we do. This one is pretty historic. This year, out at Idaho, in support of Bill Gates' TerraPower molten chloride reactor experiment, we created high-enriched uranium salt for McCree to run in this very secure environment, don't worry. And this is an example of the salt that we made. So I say we, this picture was shared with me by the program team, in particular Nick Smith, and it's really amazing because like you have to pull the uranium out of its metal form. We do this with a complicated chemical process. Then you melt it down. This is a very tiny amount of uranium. And then you melt it into a salt, and they put it inside one of our research reactors out in Idaho to start testing the fuel, and they created fissions in a liquid-fueled salt with high-enriched uranium for the first time ever in the world. I mean, we've had low-enriched uranium salts creating fission in reactors. We've had high-enriched uranium fuels of other kinds, but never a high-enriched uranium salt making fissions inside a reactor. We did that this year. Pretty fun. We have a lot of R&D for molten salts. I know molten salts are very exciting for people. We have test loops for corrosion. We have test loops for salt technology risks, understanding pumps and things like that that can be very hard with a molten salt. And they're all over the National Laboratory Complex to support molten salt reactor development. But most importantly, we are trying to understand every type of salt people want to use: beryllium, lithium fluorides, lithium, potassium fluorides, rubidium fluorides, et cetera, et cetera, et cetera. And so we have this huge molten salt database that we're developing with the University of South Carolina and our Nuclear Energy Advanced Modeling and Simulation group. We have a lot of stuff going on. It's a huge program. This is just one of my many sub-offices in my office that does advanced reactor technology research. We also do fuel cycle research. We also do spent nuclear fuel disposal research. We also have a number of people doing international cooperation and collaboration. But most of this talk today has talked about the kinds of things we worry about in the context of advanced reactors. And this is what they're focused on right now, is demonstrating feasibility, advancing alloys, qualifying materials, bringing advanced reactor technologies to the forefront, and helping them meet new operating regimes. It includes that most exciting thing where we're going to get to approve a microreactor to start up in Idaho called MARVEL, but it also includes some integrated energy systems analysis for thermal energy systems, integration with like EV battery charging and all kinds of other things, and technology maturation of really clever stuff. Like the next generation moderator is yttrium hydride. So you heard it here first. Okay. I could go into MARVEL and whatnot, but I think I can see people are like fading. One thing I'll just tell you is this. The MARVEL reactor is intended to be not a power production reactor. It is intended to be an experiment to see how quickly we can prototype and develop a reactor out at the labs. We did it 52 times in ancient history, decades and decades ago out in the desert. It is a new and different regulatory environment. It is a new and different supply chain environment. And we want to demonstrate that we haven't lost the capability to do that. So we're building this reactor out at Idaho. It has Stirling engines on the top. It's got control drums instead of rods. It's pretty neato. And that's magnet, which I just referred to as an integrated energy system capability. We also support a number of test beds for reactor companies to test out some of their important capabilities, whether it's a virtual test bed that helps them simulate the things they need to do, hot salt capabilities for testing their salts, or helium components for testing their helium components. A lot of this is happening out in Idaho at the National Reactor Innovation Center, NREC. Here is the EBR2 dome. You remember EBR2. That reactor, of course, is no longer running, but the dome that contained it is available, and we are reconstructing the inside to make a test bed so you can roll in your microreactor prototype, test it out in a safe containment structure, and roll it back out again to make room for the next developer. We also have a Lotus facility just around the corner from it. That's where we're going to test the molten chloride reactor experiment. Thank you.
A lot of territory. So we have time for some questions.
Design, and they took that ball and they ran with it. And, you know, this has all been really, really fascinating, but I'm going to ask you as a scientist, but also as a policymaker, at what point, do you think at what point and what would be the time frame that DOE is going to have to basically pick a winner? That is to say, go all in on a winning design so that you can drive down marginal costs, you can drive down supply chain risks, do all of those things and really scale it. What's your opinion? I mean, is it going to have to happen at some point, not tomorrow, but at some point?
Yeah, sure. So it is straightforward in France to choose a single design and move forward with it because they are a wholly owned utility by the French government. So the command and control is there. We do not have command and control over the capitalist market that we drive here in the United States. We tend to use carrots rather than sticks. You'll see that in tax credits, you see it in cooperative agreements, et cetera. But how long can we let 1,000 flowers bloom, right? How long can we sustain this? Because you can't build out the supply chain for 40 different reactor designs, and I assure you there are at least 40 different reactor startup companies. DOE has made some down selection choices, right? We have two big demonstration reactors, the TerraPower Natrium reactor and that XE100 reactor that we are funding with really big dollars, $2.5 billion from the bipartisan infrastructure law, plus money from my office before that, and a bunch of risk reduction awardees that will either reduce their risk and try to commercialize or not, plus a number of cooperative agreements at much smaller scale with a bunch of other companies. Maybe those are going to be the reactors that go forth. Maybe we will end up seeing another reactor be the dark horse and jump in. I believe that in the next 3 years, only the reactors that have established at least 5 or 10 contracts for new builds will survive, because you have to start building out the supply chain immediately in order to not have to overbuild that supply chain. And so reactor companies that are really focused on getting contracts today and really focused on getting their design certifications are much more likely to succeed, and I think we'll see some differentiation in the next couple of years. I personally also thought that this was the case maybe 10 years ago, that there would be a lot of mergers and acquisitions, and that from 40 reactor companies, we would already be down to like 10. Turns out that hasn't been the case, in large part because there's been a lot of private interest in supporting these companies as they develop, which is a good problem to have.
I want to follow up on that question. So we were talking before that one application is to replace coal-fired power plants that are going offline. And the capacity of the reactors you need to replace them are rather lower than the PWR reactors that we use generally. So to what extent are the different designs more suitable for smaller applications or larger applications? And do any of them really scale up? So if you want to do 50, you could do 50. If you want to do 300.
It's a great question. So we released a report almost exactly a year ago from DOE assessing how many retiring and retired coal plant sites would be suitable for small modular light water reactors in the 300 megawatt range. This is representative of a few reactor designs. The NuScale reactor is a little big because it comes in a 6-pack, but you could deploy it in the 300 space. The Holtec SMR 160 is in about the right range. The GE BWRX 300 is in about the right range. The Westinghouse even the AP300 is in the right range, and a number of advanced reactors are in the right sort of range. The X-Energy XE100 comes in a 4-pack of 70-ish megawatt reactors. The TerraPower Natrium reactor is in the like 400 and something range. All of these are in the kind of hundreds of megawatts space, which is very similar to a lot of the coal plants that we see retiring or having already retired at locations where high voltage power lines are available, cooling water is available, skilled workforce that knows how to run a steam turbine, repair a steam generator, deal with the electronics of a transmission system. Those people are in those communities, and as we look at an energy just transition, we have to bring them along, and it would be very foolish to leave behind all that transmission capacity. There are very few other sources of clean energy that could conceivably replace most of those plants, and we see about 250 gigawatts worth of empty grid capacity in those locations. About 80% of those retiring and retired coal plant sites would be suitable for new nuclear. And I think the real challenge is on scale up, as you noted. I think, that's why we need to get to these sort of 5 or 10 contracts in the next year or two, because then you can get to nth of a kind and you have the excuse to build that small modular reactor factory. And once we're building these reactors more like airplanes than airports, then you get the economies of scale. If you continue to build them boutique and one at a time, you don't get the economies of scale, and then you may as well be building gigawatt plants, which are great and will also have a role to play where there's big gigawatt scale gaps in the transmission system where really large coal plants were or are going to be gone. So there's room for everything, and I'd say in the microreactor space of the 10 megawatts, I see hope for backup diesel generator replacement and support for data centers, which are both around that same size. So what design would I pick now if I were the benevolent dictator of nuclear energy? It's a really hard question. I'm probably not even supposed to say it aloud. There are lots of ways to answer this question. I think personally, there's a great deal of urgency in getting known technology on the grid in extreme quantities. To double or triple nuclear power by 2050, we have to build tons, 200 gigawatts between now and 2050. That's 200 gigawatt scale reactors. It's 600 small modular 300 megawatt reactors or more. If it were me and I were going to try to save the planet, I would probably build like at least 100 gigawatt scale reactors and then work at the margins in small modular reactor space once those factories are set up. We have to do all of it at once right now in order to get that kind of build out, but 1,000 flowers blooming is also very challenging for the supply chain. So starting with light water reactors that we already are building, like the AP1000s at Vogtle, I would love to see at least 100 more of those in the next 10 years. But it's going to be a real challenge. But it's known, capable technology. It's going to be expensive, but you may give yourself time to catch up with, factories for building SMRs. We have a few advanced reactors and small modular reactors that are getting on the grid by the end of the decade through DOE support. But we've proven that we can build AP1000s, for example. And so it would be a phased approach from my perspective.
My name is Frederica Derima, and I'm a member. And along the lines, we're talking about how we expedite kind of the pathway. What are your thoughts? And I will use the analogy from high-performance computing, which you're familiar with. So what is the, maybe another pathway will be to look at microreactors, and like we did in high-performance computing with microprocessors, thousands and hundreds of thousands now. Would that be expediting the pathway to use collection swarms of microreactors, for example?
Yeah, it absolutely. The notion that if you can get it to where you're building them at a factory and shipping them, then you start to see economies of scale. Until then, it is way more expensive per kilowatt to build microreactors. It is quite a bit more expensive per kilowatt to build small modular reactors. It's still very expensive to build gigawatt scale reactors, but as soon as you get to a place where you're rolling them off an assembly line, they're regulated at the factory, and then they're road transported to the location, then I think there's a real hope for microreactors. And I think there are a lot of applications for microreactors. There are lots of places where we just need 5 or 10 megawatts. And we're currently using fossils for most of that.
I wanted to ask you, just in general, about the costs. I mean, it sounds like the costs are incredible, particularly if we scale up to those COP metrics. Where is that money coming from? How much is this new energy going to cost people in their homes? And I know you can't answer that specifically, but are people looking at that? Thank you.
Oh yeah, we're definitely looking at that question in DOE. We released some excellent reports, the Liftoff reports. You can go to liftoff.energy.gov and see some of this analysis. I think it's critically important to think about 2 things. One, you have to compare apples to apples. Comparing resilient, available 24/7 nuclear power to resilient available renewables plus storage, or resilient available sort of fossil energy with carbon capture and storage, for example. These are clean, resilient, like available options. To get a system that is clean and resilient, you need to have a lot of these. You can't just have solar, you can't just have wind. And so comparing the cost per kilowatt hour of wind versus nuclear is not appropriate. But comparing the system costs, they start to look really nice, actually. Long duration energy storage plus solar or wind looks like in the, first of all, long duration energy storage really isn't available at scale just yet, other than maybe a hydrogen economy, some pumped hydro, for example, but nothing the kind of grid scale that we need. Once that exists, then it's going to cost in the probably $150 a megawatt hour range for those first deployments, and then it'll roll down. That's about what we're looking at for nuclear, right? Same story for carbon capture and coal, right? And so you've got to compare apples to apples, and you've got to think about the systems cost. It is extremely clear that building out as many renewables as possible, plus a significant percentage of nuclear, will have lower systems costs than trying to do it all with renewables, because of the massive cost of that extra transition for that last mile, that last 20% of the grid that needs to be resilient. So think about it as a system, and the prices actually work out pretty nicely, even with fairly high costs per megawatt hour of nuclear.
Dan Martinez, formerly at the State Department, now practicing law in Texas. Just what do you say about the two nuclear reactors in Georgia that were supposed to, on the cost question, was supposed to herald a new sort of nuclear power revival, came in 7 years over delayed, and something $17 billion over cost? I mean, how did they pick the wrong technology? Or the wrong model?
No, it's not a technology issue so much as a mega projects problem. Whether it's the Boston Big Dig or building an airport, it is extremely hard to build multi-billion-dollar projects, especially in the United States. Those same reactor designs were built quite quickly in China. Actually, same reactor design, different structure around building stuff in mega project sizes, right? It is certainly, I think, still a great thing that we've done this. At this point, with electricity prices and the need for baseload generation that's clean, we are really lucky to have Vogtle 3 turned on and Vogtle Unit 4 turning on really soon. At peak, this project required 8,000 skilled crafts trades workers, right? Vogtle in Georgia was huge. It was a massive employment capability and therefore also very complicated. What we're learning, and the Loan Programs Office in DOE is engaging in a lessons learned activity to make sure that, new builds are following on from what we've learned from these builds. One key feature is the need for integrated project development and a sort of shared liability on delays between not just sort of the main couple of entities building the reactor, but all of the contractors and subcontractors and companies need to really stick to their timelines, or else there's skin in the game that they lose. That is critical. But fundamentally, there were also some just key challenges that are fundamental to mega projects, whether they're nuclear or otherwise. Airports go over budget and over schedule too. This is just another really big multi-billion-dollar project that's first of a kind.
We have two questions from the web. The first from Dave Rabinowitz, who is a member. Dave says, I've heard current reactors use their original controls because updating would require recertification of the entire reactor. Is this true, and is there a possible workaround?
What a wonderful question. And yes, in fact, it is true that analog control rooms are the standard, and redoing them in digital control systems would make maintaining them much easier, because a lot of those widgets and diodes and whatnot are now no longer available from the companies that originally provided them. So it can be very expensive to continue to maintain them. The NRC, however, the Nuclear Regulatory Commission, licensed these reactors with those particular control features, particularly analog controls, rather than digital. Maybe this recalls your self-driving car lecture from your last lecture. We try not to do that in nuclear energy. in DOE, we are supporting a digitization project at a nuclear power plant where we are walking through the full digitization of a control room at an operating nuclear power plant to be fully digitized and licensed by 2026 or 27. And so the rest of the fleet shouldn't have to pay that sort of first mover cost on recertifying the control system. DOE is working in collaboration with the operator to get them there for the first one, and then all 92 other reactors can follow. Well, actually, Vogel's already pretty digital, so 91.
Indeed. So the second question is from Jorge Aponte, who is a non-member. He wants to know if Artemis will use any of this technology in the near future.
Oh, the NASA propulsion modules. Yeah, so possibly. Some of the technology that we use in microreactor space, we actually stole from the space reactor universe, like the Stirling engines in the Marvel reactor that execute its, electricity generation. We stole from, I say so, we borrowed from NASA. When government agencies steal from each other, it's called borrowing. And so, yeah, I think the same thing will happen in the opposite direction. Our microreactor office supports and everything that's going on in NASA in the nuclear space, and our hope is that everything we do will be sort of shared to the extent possible.
My name is Sato, and I'm from CSIS. And could you give me some more information about the fuel supply, actually?
Yes.
It's, I understand that now that the HALEU also is heavily rely on the Russian situation. So how do you have any plan to develop these points? Thank you.
We do. So I talked to you very briefly about enrichment. Standard conventional light water reactors use 5% enriched uranium-235, more or less. A lot of these smaller designs get small and have excellent passive safety, in part by using a slightly higher enriched, low-enriched uranium. In order to avoid saying enriched twice, we call it high-assay low-enriched uranium, HALEU. HALEU supply is a challenge because the only commercial scale supplier in the world of high-assay LEU is 10X in Russia, who we no longer trust to provide uranium for our critical reactor capabilities. So we have supported, over the last many years actually, somewhat presciently, a project in Piketon, Ohio to stand up a new commercial capability by the company Centrus. They have recently produced 20 kilograms of HALEU, and they are continuing to produce HALEU at the 900 kilograms per year rate. This is not sufficient for the whole advanced reactor build out that we would like to see, but it will be supportive of some of the advanced reactor demos that I listed before, many of which do rely on HALEU, but we are going to need to scale up more than that. Also, I should note about 20% of that 5% low enriched uranium that we use for our existing nuclear reactor fleet, that reactor fleet which provides 20% of our electricity, about 20% of that fuel comes from Russia as well. There are other capabilities in the world, but we do need to expand those capabilities. We've been working a lot with a lot of our allies, and we're working towards more funding towards this expansion. The president has included a request for $2.16 billion in the supplemental request to Congress. And we think it should be paired with an import restriction. An import restriction did make it unanimously through the House this week, but it is currently stalled in the Senate. What is France's situation? France is a strong enriching capability of their own, and in fact provides fuel sufficient for their own fleet as well as others in Europe. And we are working certainly with France, the UK, Japan, and Canada to ensure that we have a kind of allied supply and expansion. We announced at COP that we intend to identify $4.2 billion worth of investment in the next 3 years in that expansion.
My name is Scott Matthews. I am a member. You've talked a lot about advanced reactor design. Can you say anything, or is your department interested in advanced fuel storage design for high-level waste?
Yeah, absolutely. So, our reactor office is just one of many offices. My office also includes an office, sub-office on spent nuclear fuel disposition and disposal. Our office is responsible for the disposal of commercial spent nuclear fuel. Not only do we have a research and development program on integrated waste management systems, including storage and transportation technologies, but also the social license that we need to identify a location to consolidate interim storage. Right now it's stored 70 plus locations all over the country, and it should be consolidated into one or maybe two locations and taken title by the government, which is part of a contract that we signed with all the utilities. The utilities producing nuclear power paid for every kilowatt hour generated to have their waste taken off their hands in 1998 by the Department of Energy. We did not succeed at doing that. It was quite a long time ago. In 2013, they sued the federal government, and the federal government lost. And so because it costs a great deal for them to continue storing that material on site for much longer than they had planned, the federal government pays out of a judgment fund about $1 billion per year to continue the current status. It would be wise for us to consolidate all of that, take title to the fuel, amend our responsibilities, reduce that liability. But it requires a community to be comfortable with either expanding their current interim storage facility or becoming the site of a new interim storage facility. So we've executed a consent-based siting process that we just began this past year by releasing $26 million worth of funding to various organizations intending to improve information around this space and identify ways to evaluate the appropriate sites. So this consent-based siting process worked well in Finland to find a repository. It's working in Canada to find a repository, and we just want to use it to find an interim storage location, which is much less complicated technically, but maybe quite a bit more complicated socially here in the US. We shall see. Thanks.
My name is George DeVoe. I'm a brand new member, first meeting. Good evening. My question is really kind of simple, but it's a two-part question. If I name 5 companies, Exxon, Aramco, BP, Shell, Chevron, each of those companies makes between $5 and $40 billion every year, every 90 days. What are they doing? They're used to building large, complex, dangerous projects. They use about 10% of the energy they sell internally. What are they doing in this field, and have you reached out to them?
I have had some interesting conversations in the petroleum space. As you may know, the Secretary has a Petroleum Advisory Committee, and through that committee, I am able to have some interesting conversations with some of the leaders in the field. Many of them are interested in being part of the supply chain. As you note, they're capable of building really big, complicated things. They use a lot of pipes, so do we. And ultimately, too, they've mastered modularity in a lot of their projects, which I think is a real lesson to be learned. In terms of them decarbonizing some of their locations, there are parts of this universe, and I will stay vague, who have expressed interest in microreactors to power some of their extraction capabilities so that they can effectively sell carbon-free petroleum. But think about it, right? Petroleum is used for a number of different things. Making plastic, whatever, a lot of stuff. If you are going to sell a carbon-free item and retain that stuff without ever releasing the CO2, then there's a universe in which you could conceivably get away with naming. It's not quite as egregious as it first appears. Thank you. Thanks.
Yep. Before you go, we have a few small gifts as a token of appreciation for your spending all this time putting up with our technical glitches. So they are a framed copy of the announcement of your talk, a ribbon, the PSW ribbon, which is emblazoned on its edges with the 3 bands of the symbol for induction, because our founder, Joseph Henry, was a student of induction and determined many of the laws of induction, and a copy of Volume 1 of the Bulletin of the Philosophical Society of Washington, right, covering the meetings beginning on March 13th, 1871, when it was founded, including the address of the founding president, Joseph Henry, on why the organization was founded, on what scientific discourse should be like, and a list of the members who were the founding members. You'll also find a fascinating article on how to calculate pi to 30 places, among other things. So thank you very much for spending time with us. The spring schedule is in a nascent and inchoate form, but keep checking the website. In a few weeks, we should have posted our first lecture of the new year, 2024. And we have a couple of people who have scheduled. Eric Klein is coming back to talk to us again. Some of you may know Eric from his talk on the collapse of the Bronze Age civilizations in the Mediterranean, which is quite popular on our YouTube channel with over 40,000 views. And then we have David Spergel coming. David is the president of the Flatiron Institute and the Simons Foundation. Oddly enough, he's going to be talking about, what do they call it now? In my day, we call it UFOs. Today, we call them unexplained aerial phenomena, UAPs. So that should be an interesting talk. He was chairman of the commission that recently looked at the Air Force's declassified information on these phenomena. So we are having a pool to take a bet on whether or not he says there are such things as aliens flying around in the air, or he'll just say that there are phenomena that we can't explain. And with that, I'll accept a motion to adjourn the 2487th meeting to the social hour. Thank you, Bob. Do we have a second? All members in favor? All members opposed? The meeting is adjourned.